In this video, we will get down into doing the tensile testing the right way. So grab your lab coats, let's get started. The key to accurate results in a tensile testing is in the preparation. And the first step is choosing the right sample. And now what do I mean by that? It's not just the length or the width of the sample, but the direction from which you take the sample can have a huge impact in your test results. And that is why it is important to check for the longitudinal direction of the sample. And this direction is the direction of rolling and the direction of the greatest extension. In most cases, this is along the length of the sample, but it's always good to double check with the manufacturer of the plate. And now I'm going to show you how to take out a specimen from this plate to carry out the tensile strength and elongation. The reference standard that we will use is ASTM A370, although other British, Japanese and Indian standards follow a similar principle. The first step in the machining process is to cut the plate to a manageable dimension that will make it easier for machining. This is typically about 200 mm in length and 50 mm in width, although smaller specimens are allowed. The next step is to take the sample through a milling operation that will help to achieve the fillet radius and the required gauge width and length. And there we go. We are done with the machining process, all ready to go for testing. There are a few key dimensions that you need to be cautious about before you get into testing. So the first dimension is the gauge length, which is where we're going to calculate the elongation from. The next dimension is the entire length of the radius section, which is a little more than the gauge length. And the standard says that it should be a minimum of 60 mm. What's also important is the fillet radius, and this is kept to a minimum of 13 mm to avoid any stress concentration effects. The final dimension is the length of the gripping section. This should be kept to a minimum of 50 mm so that you have enough material to hold on to without any slippage. And if you haven't noticed already, the thickness of the specimen is the same as that of the plate. And we're good to go. Alright, so you've started the test, and as you can see, the graph of the stress versus strain is displayed by the software. Any convenient speed of testing may be used, up to 1/2 of the specified yield point. Beyond this point, the speed of separation should not exceed 1/16 inch per minute per inch of reduced section. The slope of the tensile graph increases with increasing speed, so it is critical to be within this limit. When you're going for the stress control, ensure that your rate of loading is between 70 megapascal up to 690 megapascal per minute. The initial part of the curve is linear and follows the Hooke's law, which says the stress is proportional to strain. The slope of this part of the curve gives the elastic modulus, also called as the Young's modulus. The yield strength is the stress beyond which the material starts to deform plastically. This occurs right after the proportionality limit, which is when the curve is no longer linear. In some materials, the yield stress can be visually seen in the curve where a knee or a blip occurs. However, we do not see that phenomenon in this case. A common method to determine the yield strength is through the 0.2% offset method. A line parallel to the proportional limit is drawn at an offset of 0.2%. The stress at which this line intersects determines the 0.2% proof strength. Once the yield has been reached, the extensometer is removed as a safety precaution by holding the load for a few seconds. This is why you see the flattening of the curve. Beyond the yield strength, certain materials start to strain harden, leading to an increase in stress levels. In this region, necking of the sample begins, and we can see the reduction in the cross-sectional area. The sample sustains a maximum stress level after which the strain hardening can no longer overcome the stress that builds up due to the reduced cross-sectional area. The sample ultimately fails. Most controllers record the maximum load sustained by the sample. The maximum load divided by the cross-sectional area gives the tensile strength of the sample. To calculate the elongation, place the broken samples together and measure the distance between the gauge marks. The elongation is the increase in the length of the gauge length expressed as a percentage of the original gauge length. It is crucial to provide the elongation in terms of the original gauge length. Measure the change in width and thickness of the smallest cross-section. The percentage difference in area of the reduced section to the original section provides the percentage reduction of area. This is a measure of the ductility of the material. And for the next section, we're going to carry out the tensile test of this heavy rod. Just like we saw in the earlier case, we are going to cut the rod into a smaller section to help with the machining. Next, we are using the CNC turning center to get a fine tolerance on the machining. The key dimensions here are equivalent to that of the flat specimen, where the gauge length is controlled to be 50 mm, the fillet radius, the gripping length are all as per the standard, which is given below. And now we're ready to go for the testing of the round specimen. We start off by marking the parallel length with ink. This makes it easier to identify the punch marks. Next, we measure the punch distance, which is 50 mm in this case, using a vernier, and mark 2 sets of punch marks from either ends. We are now loading the specimen onto the UTM by ensuring the right wedge grips are being used for this diameter of the sample. As you already would have guessed, we are going to attach the extensometer onto the specimen. Now we start the testing, keeping in mind not to exceed the maximum speed as specified by the standard. Once the yield point is reached, we can now remove the extensometer as a safety precaution. Beyond the yield point, we can once again see that the strain hardening takes place on the sample, and we can visually see the reduction in the cross-sectional area. Just like in the earlier example, we can identify some critical points on the curve like the yield point, the ultimate tensile point, the Young's modulus can be taken, and the 0.2% improved stress. Unload the broken sample, once again fit them together, and find out the distance between the punch marks again to calculate the final elongation. The elongation is the percentage difference of the final versus the initial punch mark distances. Measure the final diameter of the minimum cross-section to calculate the reduction in area. Click on the link in the description below to get a free PDF of this test method. If you enjoyed the video and learned about tensile testing, be sure to like the video and leave a comment below if you want to see any testing related content in future.